Okay, last session. So we'll have first Clay Thomas, and then Simon will give 2 talks. So Clay, the stage is yours. We're going to talk about self-explanatory strategy-proof mechanisms.
Thanks. And this is joint work with Yannai Gonczarowski and Ori Heffetz. So everybody loves strategy-proof mechanisms. It's this classical and really beautiful property that theorists really like to say gives you no reason to strategize at all. But this isn't really how it works out in practice. By now, there is well-documented evidence that in practice, people play their theoretically dominated strategies. For just 2 examples, people underbid pretty frequently in strategy-proof second-price auctions, and they might rank their so-called safety schools higher than they actually want them in strategy-proof matching rules. So a major thrust in the mechanism design literature recently is this framework of so-called obvious strategy-proofness, OSP mechanisms, which argues that some interactive mechanisms can better convey strategy-proofness than others. For example, ascending price auctions instead of a sealed bid second price. And this is a really powerful framework. I really like how this framework conveys strategy-proofness, but unfortunately, a pretty big body of work has found this framework to be quite restrictive. OSP mechanisms are particularly rare, and particularly relevant for this talk, they're impossible for most real-world school choice mechanisms. So our biggest departure point from the theory of OSP mechanisms is not to think about different interactive mechanisms for the same social choice rule, but to think about different ways to describe a fixed mechanism, specifically a direct revelation mechanism where everyone reports their types TI to the mechanism up front. This is something about which previous theories provide no guidance. In particular, we study a canonical and actually quite easy to define framework for changing the description of any strategy-proof mechanism. This change describes the mechanism to one player at a time, and in doing so, we move from kind of an all-or-nothing approach in obvious strategy-proofness, where a mechanism either existed or didn't in OSP implementations. Our framework gives shades of gray. There's always some option, and you have to do work to find or quantify the best option. And so in this talk, I'll start with 2 simple examples, then define the general framework, and then give the main results, which hold for matching mechanisms. I'll give a new, simple strategy-proofness exposing description of the deferred acceptance matching rule, and prove a perhaps surprising contrast between this rule and other common matching mechanisms, namely top trading cycles, which says that this new description actually has to differ pretty dramatically from traditional descriptions. At the end, I'll circle back to talk about ongoing behavioral experiments we're doing with these descriptions. All right, let's start really simple. Median voting. So there are, say, just 3 voters with single-peaked preferences over some set of policies. They have a unique favorite policy each, and utilities decrease as you move further in some order from their favorite. The traditional description of this median mechanism, very simple. So the 3 votes will just be sorted from lowest to highest, and the middle vote of the 3 will be elected. And this is strategy-proof, and I think everyone in this room could figure out why it's strategy-proof. But does the description really convey this? Is it jumping out at you? I'm not really sure that it is. So here's a new way to describe it, and it's inspired by this observation that the key to verifying strategy-proofness is you have to know what'll happen if T minus I, the votes of the other players, are fixed. So let's just say precisely this. Let's say what can happen when T minus I is fixed. This inspires a new description that goes as follows. The obtainable policies will be the votes of the other 2 voters and all policies between them. For example, if other people vote for 2 and 4, the obtainable are 2, 3, and 4. And of these obtainable policies, the one closest to your own vote will be elected. And I really do think when you read this description and understand this description, and you're a single-peaked agent, strategy-proofness does suddenly jump out at you. This emphasizes that voting for your favorite policy gets the obtainable thing closest to your favorite policy, which is exactly what you want. For another quick example, consider a second price auction. In the traditional description, the highest bidder will win the item and pay a price equal to the second highest bid. So what's the analog of what we did just now for median? Well, once the bids of all the other players are fixed, there are two possibilities for me. I might win the item and pay nothing, or win the item and pay a price equal to the highest of everyone else's bid. And this inspires a new description that goes, your price to win this item will be set to the highest bid of the other players. You'll win the item and pay this price if and only if your bid is above this price. And this emphasizes that the price is really take it or leave it. You can't possibly influence this price, and reporting your true value will give it to you if and only if you want it for this price. So with these two examples, let's give the general formula. Both of these new descriptions had 2 steps. Step A uses the reports of only the other players to calculate some set of outcomes that player I might receive. Step B uses I's report to award them their favorite outcome from this set from step A. To see strategy proofness of any description written like this, just observe that your own report can't influence this set in step A, and reporting your true type TI will select your favorite obtainable set, your favorite obtainable outcome from this set in B. You really do need both of these observations, and they kind of tell you precisely what you need to know about how the outcome is calculated to verify this strategy proofness. So this is inspired by this classical definition of the menu of a mechanism. This is holding T minus I fixed, the set of all outcomes that are consistent with this T minus I. This is player I's menu. And with this definition, the outline says in step A to calculate player I's menu using only T minus I, and in step B to award I their favorite outcome in this menu. This is why we call them menu descriptions, and this is the central definition of our paper. So with this in hand, I can give more details on how this relates to other frameworks. So we're very much inspired by obvious strategy proofness, which is a very powerful but also very restrictive solution concept. It's impossible for the median mechanism I was just discussing. And you can get almost nothing for real-world complicated matching rules. Despite this, you can show that a menu description is actually strongly, obviously strategy proof for player I, even stronger and restricted form of OSP. Moreover, any strategy-proof mechanism has a menu description. To see this, just take any description for the outcome of the mechanism and run that description for every possible type that I might report separately. Among the set of outcomes that arise here, just allocate me to my favorite. This you might call a brute force menu description. So this says that when you're describing a strategy-proof mechanism to only one agent, first of all, it's pretty natural to inherently tailor this description just to the agent reading this description, tell you what will happen to you. And second of all, we can always use a strongly OSP description when we allow ourselves this. But this also points to a major difference between our framework and previous ones. We think of any OSP mechanism as simple to play. But not every menu description is simple. For example, this brute force description seems pretty implausible and not something you could describe to real people. Also, now that we've reframed it into this problem, sort of computational thinking gives us a really powerful language for reasoning about how simple you can make these. Despite this, and despite the fact that menus are pretty well studied in the literature, the technical questions we get when we embark on this framework are quite different than previous studies. And this is because when you shift from trying to analyze a mechanism in terms of its menus to trying to define a mechanism in terms of its menus, you just really have to ask completely different questions. And in particular, there were no known results characterizing menus for the matching mechanisms I'm about to start discussing. So with this in hand, I'll give the main positive result, a menu description of deferred acceptance. In this model, let's say we're matching students to schools, and purely for simplicity, we're doing one-to-one matchings. In these mechanisms, students report types TI, which rank the schools supposedly from favorite, second, third, and so on. In this setting, schools are non-strategic, so we call their preferences over the students their priorities, and let's think of them as determined by set-out policies the schools can't strategically report. And the single most popular mechanism in these settings is deferred acceptance. In the traditional description of DA, students propose in order of their preference lists, schools look at the proposals as they get them, and they keep the highest priority proposal they've seen so far, and you continue until everyone finds a match or proposes to everywhere they ranked. And this is a really useful mechanism. Stability is important. This gives the student optimal stable outcome, and if you want a strategy-proof stable outcome for the students, this is actually your only option. So all this leads it to be really popular in practice. Unfortunately, its strategy-proofness is really quite challenging. If you're giving it to undergrads and doing a full proof, it could take you more than one lecture, and it's certainly not something you could hand-wave to a non-expert. So the question is, can we find a menu description? Unlike the two simple examples I gave at the beginning, it's really unclear how to characterize this menu. But nonetheless, here is our menu description of DA. If we hypothetically run school proposing DA without you included in the market, you earn admission at every school that prefers you to their hypothetical match. And then you'll be matched to your highest ranked school on your list where you earned admission. So our theorem says this is a menu description of student proposing DA. Despite the fact that we've used a school proposing algorithm in step A, this gives you your match in student optimal DA. It doesn't give the match of any of the other students. The hypothetical match here can be virtually unrelated to their actual match in the mechanism. So this description doesn't tell you how the school district is actually going to compute matchings. They will probably use a optimal n squared time algorithm for doing this. It does tell you precisely who you will match to. Despite this, it's nearly as mechanically simple of an algorithm as traditional DA, adding a hopefully even intuitive menu picking step on top of a run of school proposing traditional DA. And yet its strategy proofness is something you can verify for yourself. You can replace advice that says things like, look, famous Nobel-winning economists have proven thou must not strategize, with the observations that hold for any menu description. You can't influence the set computed in step A, where you earn admission, and your true preference ranking gets you your favorite obtainable school in step B. So I'll actually briefly pause here and take any questions, especially clarifying questions from the in-person audience. No pressure, but yeah, I'd be happy to take one or two. Yeah.
Yeah, sorry, this might be naive. When we run school proposing DA, does it require everybody else's preferences?
Yes. So take the market where I'm not there. No school will propose to me. But you need to know other people's preferences. For example, if they get two proposals from two schools, what will they pick? So it's a standard run. We've just flipped the market and taken me out of the market in that step A. Yeah?
But you're telling the agent, this is what I'm going to do behind the scenes, and then I'm giving you a cutoff in each school, and now you decide that you don't know these cutoffs in advance. You know that there's going to be cutoffs.
Yeah. And interestingly, the cutoffs can be different for different students in a fairly complex way. But I won't get into that for this talk. OK. Yeah?
So in practice, would you, if you wanted to show some students, prospective high school students, a menu, would you just simulate the DA, given what you estimate the preferences to be, given what previous years, what the preferences were in the previous years?
You could do this. You could try to estimate what the person's menu will be, and that could help them. But that's a really complex, I'm not sure how that would influence equilibrium behavior. And that's beyond the scope of what we're trying to do, which is just an ex ante, a strictly ex ante new algorithm and new way to understand the process. Okay. Yes?
I still don't really have the intuition for why we run school proposing.
Mm-hmm.
One reason is it's known from Azevedo Leschno that we have like score description and market clearing description of DA. And
So
there you run student proposing and you get the scores, and I wonder why we need school proposing.
it has to do, I won't get into precisely why, but it has to do with the rural hospital or lone wolf theorem. For several reasons, the Azevedo and Leschno framework is very incomparable to ours. They do like average case, very large markets, and this is worst case. The cutoffs that they describe would very much not suffice in worst case markets. In particular, they have linearly many cutoffs. We can prove you need quadratically many cutoffs. But that is a bit technical, and I should move on to the hardness results. So this is a nice menu description. We like it, but did it have to look like this? There's a lot of questions still remaining whether we could make it simpler. And to kind of tell this story, I'll use two other matching mechanisms. First, serial dictatorship. This is a very, very simple but often desirable mechanism, and you can prove its strategy proofness even to undergrads in just a minute or two. In the traditional description, this goes in some fixed order over students, and you permanently match the students to their top-ranked remaining school. So to see its strategy proof in the language of this paper, it just already is a menu description. But more is true. It's a menu description for every player at once, and it uses the menu description as a step to calculate the matching. So what a student needs to know from a student's perspective, the process goes, it starts with a menu description, and then it proceeds to calculate the rest of the matching. And this also proves that it's OSP. Let's look at a more complicated mechanism now, top trading cycles. This is yet another canonical mechanism that's not quite as popular as DA in practice, but is still very useful. And for simplicity, let's say that each student starts endowed with a school. It generalizes to priorities, but for now, let's say I is just endowed with school I for each I. And for this setup, you could probably prove in 15 minutes in lecture that this mechanism is strategy proof. Let's see a reason that this is the case. So the traditional description has students trade their endowed schools in cycles. Each I points to the student endowed with their favorite remaining school. In this DAG, there must be some cycle. Pick one, permanently match everyone to the school they're pointing to, and remove them from the market and recurse. A known key lemma is that this is well-defined and it's independent of the order in which I select cycles. So here I can see it doesn't matter if I do 5, 6 first or 2, 3 first, I get to the same state after matching both of those cycles. So now with this lemma, consider the following run of TTC. Fix a student I, and as long as possible, match only cycles not involving I, or equivalently, everyone points except for student I, and you keep matching cycles as long as you can. Now, regardless of where I will point, it must form a cycle. So match this cycle, and in doing so, match I to their favorite remaining school. Then continue with the rest of the cycles in any order you like. This particular run of TTC, we formalize to say it goes in step A, matching all cycles not involving I, B, matching I to their top remaining, and C, calculating the rest of the matching. So A and B form a menu description, but again, like serial dictatorship, more is true. This ABC outline overall uses the menu description to compute the final matching. With these insights in hand, we can now go back to DA. So within TTC, we found a menu description. Our impossibility result says that this isn't the case at all for DA. We prove that nothing close to DA could possibly fit this 3-step ABC outline that finishes with computing the matching. So how do we formalize this? What is close to traditional DA? First, this algorithm is student proposing. It reads these preferences through once in favorite to least favorite order. And second, it works by just kind of tweaking some tentative matching. You have some matching stored in memory and perhaps a bit of extra supplemental data, but you just tweak this as you go, and this is as low as possible because it's roughly the size of the output matching. And it's far less than the total bits of the input, which is quadratic, since each of the n students have an n-length list. And in addition to descriptively saying how DA traditionally works, it also is harnessed by real people to explain DA in practice. The fact that the preferences are read in such an order, and the fact that it just tweaks a matching as it goes, this is how people describe it. So what does our result actually formally say? It says that any student proposing algorithm for student optimal DA fitting this three-step outline that does a menu description and calculates the outcome. This requires memory n squared. This nearly matches the trivial bound of memorizing the entire input, and while I can't be sure what you're doing with this n squared memory, you're definitely not just tweaking some tentative matching as you go. You're storing a lot. And this proves that no small modification of traditional DA can reveal the menu, ruling out a pretty large class of menu descriptions within traditional DA. But what I think is really interesting about it is what it says about the traditional descriptions. It says that the menu, or more precisely the fact that you get your favorite thing from some set you can't control, it says that this menu is very hard to infer from the traditional description. This says that DA's strategy proofness is hard in some way that TTC's is not, and it shows the tangible benefit of switching to a menu description where this menu is now very easy to see. Just to tell the story one other way, serial dictatorship was OSP and our life was kind of easy. We could explain strategy proofness with one mechanism to all agents at once. TTC was provably not OSP, and in some formal sense, thus we needed to explain strategy proofness separately to different people. But conditioned on this, things were basically as nice as possible. A tiny change to the traditional description explains strategy proofness to any agent you like. But DA, it turns out, is just a hard mechanism. There's no silver bullet that will do this as well as TTC, and you really need a dramatic change to explain strategy proofness via menu descriptions. So this is the main impossibility result, and I'll take another maybe roughly one question before moving on, if there is any. Yeah. Federer, right? Sorry.
So what about the inverse problem? So here you start from a mechanism and you define the menu description. What about turning it other way around? So we start from a menu description, so for each agent and each realization of types of others, we create a menu. Can something be said when this combination of menus is feasible if it corresponds to some mechanism?
Right. I think that could be a very interesting approach. We already know that DA is like probably the mechanism we want for many settings for other reasons. It's just really nice of a mechanism. But there might be settings where you could invent a new mechanism by looking at what menu descriptions could be like. I'd actually be happy to talk about that offline. I don't know of any result like that so far. I might move on. I won't cover the proof sketch except to say I'd love to give it offline. I find it very crisp and really, really nice. So there's one more kind of aspect to this hardness results that are important, so I'll quickly go over this. And that's the fact that there are more ways to describe DA, student optimal DA, than what I've talked about so far. The results I've talked about so far fit into the following classification. They might describe the matching, they might describe the menu, or they might fit this ABC thing that describes both. And they might be student proposing algorithms, or like the menu description, the main positive result, they might be a school proposing algorithm for the student optimal match. And so this leaves several more possible descriptions that fit the rest of these boxes. And perhaps surprisingly, all three remaining possibilities exist. We construct these with memory nearly matching that of traditional DA. but unfortunately they're terrible. They're really, really delicate, really hard to describe algorithms. So the last thing we do is prove a formal sense in which all of the remaining algorithms that I haven't covered in detail must be convoluted. Specifically, it's a non-locality type of property where I have to update information about school J when making queries not really related to school J. And so with truly simple one-side proposing algorithms, the two options are traditional DA or the new menu description that I described. Traditional DA explains the matching, explains the fact that the matching is one-to-one, and it explains even stability quite well. But these are the concerns of the policymakers and the mechanism designers. Our new description explains strategy proofness, the concerns of the students actually participating in the mechanism. So maybe I'll take questions about this part of the theory offline so that I can talk about the experiments. So first I'll give a bit of experimental related work. There's a beautiful, pretty new line of research with inherently behavioral explanations of seemingly irrational behavior, things like loss aversion causing you to play irrational seeming, really conservative strategies. But our paper is more in the vein of OSP, which talks about the decision-making process of the agents. And one very interesting empirical related work here shows that framing a mechanism as obviously strategy proof, specifically an ascending auction with a video animated feedback that shows an ascending price, despite the fact that the auction is actually static and people submit sealed bids, they show that this can get you results nearly as good as actually running the dynamic ascending price auction. So this is extra motivation for our approach, which frames the mechanisms as strongly obviously strategy proof. But by far the most closely related work is this working paper by Katushkak and Kittsteiner, who also suggest describing a matching mechanism, TTC, with a menu description. So it's worth saying precisely what they do. They tell participants that some set will be calculated using T minus I, and then that you will be matched to your favorite ranked available school in this set. And then in an appendix physically handed out to the participants in this experiment, they say that the way that this step A is calculated is by running TTC separately to check if each school is available, independently running TTC n times. Very close to the brute force description I gave at the beginning. And this is really promising, really pioneering work that we like, but we really think you need a simple way to compute the menu if it's going to be practical, so that's what we're studying. And to the best of our knowledge, this is actually the only other paper that experiments on equivalent descriptions without changing the feedback or the strategic advice. So there's a lot of room to do stuff here. So the premise of our experiments was to test the two simple mechanisms from the beginning of my talk, median voting and a second price auction. We described the environment to the participants. We described the mechanism to half of people with traditional, to half of people with menu. We checked participants' understanding with examples and with comprehension questions, and then they played 10 rounds of the mechanism for real money. And in median, we get pretty promising results. The fraction of rounds where people play their dominant strategies statistically significantly goes up from 70% to 80% on average. And while it's not statistically strong, it seems that this is actually helping people earn more money and play this same game better. Looking at the histogram, the distribution of the fraction of the 10 rounds where people played their dominant strategy, we can get even more robust results. You see it's pretty flat for traditional compared to menu, where quite a lot of people are voting for their peak in all 10 rounds, and we get a really statistically strong increase there. For second price auction, we actually get a non-result. Basically every statistical test we could throw at this would show there's no difference between the two descriptions. And of course we don't know precisely why this is, but looking at the comprehension questions actually gets a really valuable insight. The menu description seems harder to understand. Possibly overall, a few more people make any error in the comprehension questions on first try overall. But definitely in a specific way that a lot of people looked at the example and wrote down their own bid as the price they would pay. And this was a specific thing we hoped our menu description would dispel and clarify. So this may indicate that the description just needs further refinement, but also our framework overall just gives some new proof outline that you can transplant onto any strategy proof mechanism. It may be the case that, especially for really simple mechanisms, it's actually not easier to see this new proof outline than the really simple starting proof outline. Looking at these comprehension questions for median can get us valuable insights as well. In these questions, the traditional description had people sort the 3 votes. The menu description had you write down the entire menu, which seemed, again, slightly harder to actually do. The fraction of people making mistakes went from 12% to 32%. But what's really interesting is that people who got the things right first try are playing really, really well, with a statistically strong correlation between getting these questions right on the first try and voting for your dominant strategy. This goes up to 87% with the people who got it. And looking at the histogram can really kind of show you what's going on. The people who don't quite get the mechanism are playing this flat, pretty arbitrary strategy, but people who get it are playing really well, suggesting that the difference we see overall is driven by the comprehension and understanding of the menu description. All right, to quickly wrap up, we give new strategy proofness exposing descriptions of key mechanisms. We're developing experiments for DA right now. These can replace complicated proofs and thou must not strategize type of advice with the same easy proof outline in any mechanism. And our impossibility results give rigorous senses in which traditional descriptions of DA were in a wrong corner solution between the trade-off of exposing strategy proofness and describing the full matching. This gets us a pretty rich set of both theoretical questions and interesting experiments, and this is something I'm really excited for, and I think really the sky is the limit. I think explainability should be a really important desideratum in market design, and I'd be happy to talk about any realization of it, and I think it's an avenue for formal reasoning going forward. Thanks.
Questions?
So is the paper published as named in the description? Because it said self-explanatory, and I really like this language here, strategy proofness exposing. And I would suggest that that might be the more direct description of what you're doing.
I actually quite like that too. We hadn't thought about it.
You thought about it a little bit because it's on your slide, but yeah.
Well, that's a good point. It's not online yet. Hopefully in a few weeks it will
Great.
be.
I would suggest it, but thank you.
So in the NRMP, they recommend participants to submit their true preferences because it's strategy proof, or I don't know what. I think they have a video showing.
Yeah.
Yeah. So one thing that is, if I'm a participant, I might think that how can they do the best for me and the best for you and the best for someone else at the same time? And here, in your description of DA, I might think the same. Even though there's cutoffs now, how can you give everyone what they want? Maybe
so it's a very good point. To some extent, we require really strong trust in the mechanism designer, the person running the school choice mechanism or whatever. You have to still trust them that they're giving you factual information about what the match could be. But it feels really significant to us that you've now shifted from thou must not strategize type of, Al Roth proved that you shouldn't, to now something that you can see for yourself, conditioned on believing this factual information, this information about this is who you will match to. And this type of factual who you will match to information is what we're used to and comfortable with already trusting the school district about. If we don't trust them that they're going to run DA instead of SD or just a fixed matching, then we're already kind of lost for this framework of improving trust and improving understanding. So yeah.
Maybe.
So in student proposing DA, for an individual student, for any preference rankings of all the other students, there will be some set of schools such that the student will be matched to their favorites, the top-ranked school in that set.
That's right.
So how is that not count as a simple menu description in your model?
Okay, so you're more or less saying, let's not tell them exactly how we'll calculate the set. Let's just say some set exists, right?
Yeah, or certainly you could tell them what the set was like ex post.
Yeah, we really have an ex-ante viewpoint, first of all. Like, we want people to understand before it starts. And we don't want people to say, like, oh, actually, I wanted this from my menu after seeing my menu. Because that might break all sorts of other things for other participants. But let's think about this proposal, that you tell the participants some set will exist. This doesn't tell me anything at all about the mechanism. This is not, in any sense, a description of what I will actually match to. I haven't differentiated between DA, SD, or even the constant or randomized mechanism where I toss all the schools in the air and assign you to a fixed thing. So it's probably actually a useful thing for a school district to do, to give it at a high level that some set will exist. But it's not what we're in the business of today. We're describing what you'll actually concretely be matched to. And yeah, that's the point of our paper.
Oh, I see. Okay.
But it might be a useful alternative definition of strategy proofness that might, we have no idea, but it might be easier for real people to just grasp mathematically what it means.
Okay, thank you.
Yeah?
Thank you. Yeah, other questions? By the way, what the results from the TTC paper in their experiments? Did they show and find any improvement?
Yeah, a pretty strong one. Like, they designed kind of really tricky priority structures that, you know, were supposed to make people think there would be a big conflict. So they had super low proportions of straightforward behavior, something like 10%, but it went up to like 20% with their black box menu description as well. So pretty promising. And also giving credence to this sort of black box suggestion as a useful thing to do.
Okay.
All right.
Thank you. Simon. Thanks a lot.